So again, we're dealing with a two-sided test today. The wording in the problem will say, is it different now than what it was? And that'll help us write our hypotheses. So according to the National Center for Health Statistics, 12.3% of all births in the U.S. were to teenagers in 1999. So to see if this percentage has changed this year, a random sample of 1,000 births were investigated and 111 were to teenage mothers. Can we conclude that the percentage of teenage births has changed at the 10% significance level? So it doesn't specifically say is different. Another phrase they might use is changed. So again, the first things we do is we name what's our true proportion, what's our sample proportion, and what's our alpha. Anyone have a suggestion for any of those? Good. The true, yep. Okay, which is 0.111. Yep, 111 over 1,000, so 0.111. And what's the alpha level? 0.10. Yep. All right, so I'm just going to do a little shortened version here, step one. Step one, basically we would say, well, it does appear, doesn't it appear that the percentage of teenage births has changed? Is this different from the true value? Okay, and is it greater than or less than? It's less than. Okay, so we would say that, yeah, it appears that it has changed since the new value is less than the true value. And the reason for that, though, could be sampling variability. So what we're going to do is we're going to do a one sample z-test for the true proportion of teen births. So that's what we're going to do at an alpha level of 0.10, 10%. So we're allowing ourselves an error of 10%. So now step two is our null hypothesis, which would say that the true proportion is 12.3, that it hasn't changed. The alternative hypothesis is that it is not 0.123. It is different. It has changed. It doesn't say go up or down. Now, there's a little note at the bottom of this. If you look down at the bottom of this, I'm just going to invite you to look at that right now. It says, always base the alternative hypothesis on the wording of the question, not the results of the sample. Because in reality, if you were doing a hypothesis test, you've already decided your hypotheses before you collect the sample. Okay, so the question says, has it changed? That's why our alternative is not equal to, even though our sample is evidence that it's less than. That actually tells us which one we choose in the probability question. All right, so now we're on step three, and what is step three in writing a hypothesis test? Thank you very much. Thank you. So what's step three? Checking the conditions. So condition number one, so we're going to check our conditions. So condition number one, it's stated as a random sample of births. Stated as a random sample of births. All right, second, is 1,000 births less than 10% of all births? Yeah, we can assume 1,000 births is less than 10% of all births. And then third, what's our third condition? Large sample size, which in this case is that n times p is greater than 10 and n times q is greater than 10. So if n is 1,000 and p is 0.123, that's 123. And 1,000 times q is 0.877, that's 877, both are greater than 10. So we can assume normality. Normality is a shorter way of saying it's from a normal population, approximately normal population. Because of the large sample size, we can assume that we're dealing with normal distribution. All right, so now we're on step 4, which is doing the calculations, and this will look a lot like the problem we just went over in class. So step 4, we need to, we're actually looking for the probability that p hat is not equal to 0.111. So now is where we take our sample value. Our sample is the one that's giving us some evidence that maybe it has changed. The percentage, the proportion of teen births has changed. And we start out with just basically writing our alternative hypothesis with our sample value. Now, that's not an easy probability to calculate. We need a greater than or less than. So we're going to change this and say, well, remember the normal curve, we're looking for the z-curve, the normal curve. We're looking for the z-score below and the z-score above. We want to find both of these areas. Well, we can only find one at a time. So we say, is this less than or greater than our true value? It's less than. So I'm going to say, well, if I just focus on, instead of, I can't find both at the same time, I can find one and multiply it by 2. So twice the probability that p hat is less than 0.111. And that decision, whether to choose less than or greater than, is based on how my sample compares to my hypothesized value. So now it's like I'm just going to ignore that 2 times thing until the very end. It's just going to follow each step along. It's going to be the very last thing I do. So now this is just like a one sample test. I'm just going to say, okay, well, 2 times the probability that z is less than. I calculate my z test statistic, which is my observed value, my sample value, 0.111, minus my hypothesized value, 0.123, divided by the standard deviation, the square root of 0.123 times 0.877 divided by 1,000. Now I do that calculation on my calculator. I already have it done, so you don't need to do it. So the probability that z is less than negative 1.155. So I'm finding this side, this is my z-score, negative 1.155. What's the probability that it's less than that? So how do I do that calculation? NCDF, so 2 times NCDF. In this section over here, it's the lower side. What's the lower bound? Negative infinity is the lower bound. The upper bound is my z-score, negative 1.155. Mean of 0, standard deviation of 1. Okay, when you do that, you still haven't taken 2 times it, but you get your initial p-value should be 0.124 when you do the NCDF. And twice that, because this side, this z-score would be positive 1.155. If you did the greater than and switched the subtraction around, you would get positive 1.155. So it's the same, so we're just going to take it times 2. So that gives you your p-value. The probability that you get a sample this far away in both directions is 0.248. That's your p-value for this problem. You compare that to your alpha level. What was our alpha level? 0.10, and we put an appropriate symbol in there, greater than or less than. It's greater than. So what do? We fail to reject the null. We fail to reject the null. What does that mean in the context of this question? Has the percentage of births of teenagers changed? Oh. Okay, we don't have enough evidence to say, yes, we don't have enough evidence to say that it is different, okay? We fail to reject the null. There is not evidence to say the proportion of teen births has changed. From 1999. So there is not evidence to say the proportion of teen births has changed from what it was in 1999. All right, so a little note, when you're using the not equals in the alternative hypothesis, it is called a two-sided test or two-tailed test. The tails referring to the normal distribution, finding the tails, the ends. When we're doing a two-sided test, a sample proportion above or below the hypothesized value would give evidence against the null. Thus, when you're calculating a p-value, we must find the probability of getting an observed value as more extreme in either direction. So, in other words, how likely is it to get a sample proportion at least this far away from the hypothesized value because of sampling variability? So, and we already talked about the note at the bottom. You always base the alternative hypothesis on the wording of the question. All right. Type 1 and Type 2 errors. Once we form our hypotheses, we use sample data to decide whether or not to reject our null hypothesis. However, just like a jury can reach the wrong conclusion in a trial, it is possible that we make the wrong decision when we conduct a test of hypothesis. So, in a trial, there are two possible errors a jury can make. First, they could convict an innocent person. So, in other words, send someone to jail who didn't do the crime. Or they could let a guilty person go free. Let a murderer walk around on the street. Go back to their normal daily activities. All right, so in hypothesis testing, there are also two possible errors we can make. A type 1 error is rejecting the null when it's true. This needs to be put to memory. We're going to practice putting it to memory today too in the context of questions. So a type 1 error is rejecting the null when it's true, and a type 2 error is failing to reject the null when it is false. All right, so convicting, if we go up here, if the null hypothesis is innocent, innocent until proven guilty, right? So the null is innocent and the alternative is guilty. Okay, then a type 1 error is rejecting the null. So if the null is innocent, I reject that, and what do I decide? I decide they're guilty. So a type 1 error is I decide they are guilty but really the null was true. I decide they're guilty, but really they were innocent. A type 2 error, and I remember a type 2 error because it's got fail twice, to, fail, false. It's got fail and false, two failing, false, negatives. So it's type 2 error. Fail to reject the null. So in other words, I decide they're innocent, but really it's false. Really they're guilty. So a type 2 error would be deciding that they're innocent, but really they're guilty. So in other words, convicting an innocent person is a type 1 error, and letting a guilty person go free is a type 2 error. So what we want to look at, your job will be to make a decision or describe what a type 1 and type 2 error are in different situations and what is the consequence. So we've got a farmer here. He only grows tomatoes and supplies them to a local hamburger chain. Currently he's able to sell only 75% of his tomatoes because they have to be a certain diameter in order to fit the hamburger patty. So he's considering upgrading to a more expensive fertilizer if he can be convinced that it will increase the proportion of tomatoes he can sell. Define the parameter of interest, state the hypotheses, and describe both kinds of errors in context, including their consequences. So first of all, the parameter of interest, is the size of the tomatoes, isn't it? Size of tomatoes. But really, even further than that, it's the proportion he can sell, isn't it? Proportion he can sell. So it's the size of the tomatoes, but they have to be big enough, it's the proportion that he can sell. So then we need to decide what our null hypothesis would be and what our alternative hypothesis would be.